Okay, in this section we are going to discuss phase changes and the energy that is needed for phase changes to occur, or the changes in energy that will happen for phase changes to occur. First of all, let's start by defining a phase change. A phase change is a reversible physical change that occurs when a substance changes from one state of matter to another. Okay, so let's kind of look at that in more detail. A reversible physical change, which means that it can go back to the way that it was. It's a physical change because it hasn't changed the composition or the makeup of the substance. Okay, the only thing that has changed is the state of matter. Is it a solid, is it a liquid, or is it a gas? Okay, so that's what we're looking at when we talk about phase changes. Now, this right here is a phase change diagram, and I'm going to use this picture periodically throughout the chapter. But if you take a look at this, you'll see that what they're doing is they're comparing temperature and the energy that you're putting into the substance. And this is what's going to happen to the substance as you put energy in and as the temperature changes. Okay, so you'll see right here, if we start at point A, there's not a lot of energy and it's fairly low temperature. As we put more energy in, the temperature is going to rise. But then we're going to get to this point where we continue to put energy in, but the temperature doesn't go up. We're going to talk about why that is as we go through. First of all, let's talk about movement of energy. I'm going to have you leave some space in your notes in this section because we're going to talk about some examples of this that I'd like you to write down. But basically, energy is always going to move from areas of warm to areas of cold. Okay, never the opposite. It'll never move from cold to warm. Energy always travels from areas of warm to areas of cold. All right, so energy in a phase change can be one of two things. It can be endothermic, which means that the system is absorbing energy from the surroundings. So let's say, for example, the system is an ice cube. Okay, if the ice cube is absorbing energy from the surroundings, then energy is going in to the ice. It's causing those molecules to move faster. And as a result, those molecules will start to break their mutual bonds of attraction, as we saw in those videos we watched earlier in the chapter, and they'll start to flow past one another. And so you're going from a solid to a liquid as energy is absorbed into the system. And okay, just so you get this written down, energy is taken in and it causes the substances to move faster. Okay, if they move fast enough to disrupt the attraction between the molecules, a phase change will result. The dance of the little lumps was the perfect example of this. Okay, they started moving faster and faster and faster, and eventually they got to a point where they could no longer hold together and they fell out of their regular lattice pattern. And that was a phase change between a solid and a liquid that resulted from an endothermic experience. Energy went into the substance. Now, the other kind of energy movement would be called exothermic, which means the system releases energy to the surroundings. Or another way to think of this is to think of energy exiting the system. Okay, so water freezing would be an example of this. If you have a melting ice cube, which has enough energy that some of these molecules are in liquid form, okay, and then that energy is lost, it exits the system, those molecules are going to begin moving slower and slower and slower. And what will eventually result is the water being frozen once again. Okay, so that's energy exiting the system, or an exothermic movement. Okay, so in exothermic, energy is taken out and it causes the particles of the substance to move slower and slower, which then will cause the forces of attraction to be reestablished if they had been broken before. Now, if the forces of attraction were still intact and energy was taken out, it's just going to get colder and colder and colder. We'll talk about that again in a little bit. Okay, so temperature changes. As thermal energy is added to a substance, the temperature is going to continue to go up. You know this, you've probably done this 100 times. You put a pot of water on the stove and you turn the stove on. It is eventually going to the temperature is going to start to climb. As you put energy in, it gets warmer and warmer and warmer. But eventually it's going to reach a point where a phase change will occur. For boiling your water on the stove, that is 100 degrees Celsius. And at that point, you're still continuing to add energy, but the energy is going into breaking the forces of attraction between the particles, and so it's not raising the temperature. If you were to put a thermometer into your boiling water on the stove, you would see that once it starts boiling, when it's at that point where it's going to change from a liquid to a gas, the temperature doesn't go up. All of the energy that you're putting into it is going into changing phase or breaking those forces of attraction and not into raising the temperature. The same is true when energy is lost. If the temperature of a substance, if energy is being taken out of the system, the temperature will continue to drop until it gets to the point of a phase change. So let's say we put water, liquid water, we fill our ice cube trays and we put it in the freezer. The temperature of that water is going to continue to drop because it's going to lose energy to the surroundings, to the freezer. And so it's going to continue to get colder and colder and colder until it reaches 0 degrees Celsius. At that point, it's still releasing energy to the system, but that energy that's being released is not dropping the temperature of the ice, but it's reestablishing those forces of attraction so that the temperature is not changing. In the process of freezing, the ice is still 0 degrees Celsius, but it's reestablishing those connections, those forces of attraction. And then once those are all put together again, then the temperature of the ice will continue to drop even further below that point. So if we look at this graph once again, here we have our liquid water. Okay, and if we put this on the stove, okay, and we start heating it up, this water, as the energy gets put into it from the stove, the temperature is going to go up, and it's going to go up, and it's going to go up until it gets to this point. Now, if this is water, this point is 100 degrees Celsius. At that point, once you put more energy into it, all of the energy that you put into it is going into the process of changing it from a liquid to a gas. That's the heat of vaporization. That's the energy required to change it from a liquid to a gas. So even though you're putting energy into it here, the temperature is not going up. It's simply changing from a liquid to a gas. Once it all becomes a gas, then the temperature will continue, the temperature of that gas will go up beyond 100 degrees Celsius, but that won't happen until it's all a gas. The same thing is true with our liquid ice, or our liquid water when we put it into the freezer. Okay, we put it into the freezer, which means that we're actually taking energy out of it, and so it's going to get colder and colder and colder until it gets to this point. Now we're going to continue to take energy out of it, but in doing so, we're changing it from a liquid to a solid. We're freezing it. Okay, this is called the heat of fusion. It's the energy being taken out is all resulting in the phase change. So the temperature is not dropping here. It's just changing phases. Once we get all of that liquid water into solid water, then we can get the temperature to drop even further as we take more energy out. Okay, so hopefully that makes sense. We will look some more at that in class tomorrow.